So let me try to share my screen.
So you can test it. So we'll
You can
start at
test it. So we'll
2:30
start at 2:30
as we
Sure,
have
sure,
given
sure.
as
the
we have given
yes.
the yes.
Um, yeah, is it visible?
Yes, it is visible.
Yes, it is visible.
Um, all right. So just so please tell me when to start. Okay, I'm ready. Although I cannot see the questions, etc. I hope there will be live questions.
Sir, there is a
Sir,
option of
there is an option of that is
chat, and chat is
chat,
enabled,
and chat is
and
enabled.
they can
That is
raise
not
their
enabled
hand.
They
for
can
me.
raise
Participants
their
can
hand.
raise their hand.
Participants can raise their hand.
No, no. Once again, chat is not enabled for me. So it's saying chat in channel meetings is only available to team members.
Okay,
So
but
I
so
Okay, but
cannot.
participant can
the
raise their
participant
hand
can
and they can
raise their hand
unmute
and they can
themselves and they can
unmute
ask
themselves
questions,
and they
sir.
can ask
So if
questions.
you,
Okay,
So
if
okay.
it
if
is
you,
really okay with
if it
you.
is really okay with you.
Sure, 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 sure. So I would want it to be live and interactive, not a monologue. So I think that will be the best. Acha, I already
Okay,
see a
sir.
raised hand. Is that by mistake or is that actually a this thing?
Uh, I think
Uh,
that is by
I think
mistake,
that
sir.
is by mistake,
Okay,
sir.
okay. I see. Okay, all right. No, so this is the first time I'm presenting through this Teams, Microsoft Teams app. So so that's why. So I hope things will be okay.
It's okay, sir.
It's
No
okay,
issues.
sir. No
So we are
issues.
there to help.
We are there to help.
Thank you, thank you. Yes, please.
So we'll start in
So
2 minutes.
we'll
I'll
start
just
in 2 minutes. I'll just check. Format, I think we can start.
yes, sir.
Yes, sir.
Good afternoon, everyone.
Good afternoon, everyone.
I welcome you all
I
to
welcome
session
you all
3
to
of
session
A2.
3 of A2.
It is my proud privilege
It
to
is a
introduce
proud privilege
Dr.
to
Anna
introduce Dr.
Bhattacharya.
Anna Bhattacharya.
And there is an echo at your end.
Uh, Sir, I don't know why it is
I don't
echoing
know why it is
because
echoing
I'm not logged in from any other device.
device.
Echo is generating.
Maybe from my.
Hello.
Yes, yes, it's rectifying, madam.
Okay, sir. Dr. Anna Bhattacharya is a professor in Department of Computer Science and Engineering in IIT Kanpur. His specialization and research interests are data mining, bioinformatics, information retrieval, natural language processing, to name a few. He is a recipient of award from Yahoo under Faculty Research and Engagement Program 2011. He also received Best Paper Award at the International Conference on Management of Data COMAD in the year 2011. I welcome you, sir, to this faculty development program, and I request you, sir, to start the session. Sir, can you hear me? Arnav, sir? Hello.
Yeah, his participants, the speaker's screen is frozen. He's just logging out and logging in once again.
Okay.
Yes, Professor
Hello.
Arnab, you are in. Yes, we can
Yeah.
hear you now.
Okay. Great. Thank you. Just let me load.
Okay, so Dr. Anab Bhattacharya is here. He is a professor in Department of Computer Science and Engineering in IIT Kanpur. And his specialization and research interests are data mining, bioinformatics, information retrieval, natural language processing, to name a few. I welcome you, sir, to this faculty development program. And so please start the session.
Yes, I am very sorry for all this delay. I hope.
It's okay, sir.
Yeah. Just 1 second. Yeah, I hope you can all see now.
Yes, sir, it is visible, sir.
Okay, thank you. I'm very sorry for this inadvertent delay. I had to
It's
read
okay.
my laptop. Well, thank you for inviting me to this session, and I welcome all of you to this session. So I will be talking a little bit about support vector machines or SVMs. Now I request all of you to be please interactive and ask me questions as soon as you have a question. Okay, so you can actually interrupt me and ask a question.
Yes, Professor. If somebody who's not able to post, we are taking on his behalf on the WhatsApp group, and we'll be posting the questions as and
All
when they
right.
arise.
Okay. All right. Thank you. That will be the best. So let me move forward. So we will look at support vector machines. So, so basically the idea of a support vector machine is that this is a classifier. Okay. And we have already seen what does a classifier mean. It's basically uh, given an object, we have to say which class this is it. Now, a support vector machine or SVM is a binary classifier. So it can work with only two classes. Okay. So this is very important to understand that, and we will in the towards the end of this session, we will see how we can handle multiple classes. But inherently, support vector machine is a binary classifier. So there is only two classes. And here is an example that you can all see. So this circle objects are one class and this square objects are another class, right? Now, an SVM is what is called a maximal margin classifier. And we will look at each of these terms separately. So first of all, it is a classifier. Of course, we understand that. Now, without looking at the slide and any such thing, suppose I tell you that please draw a line that separates these two things. Now, as you can see that there are multiple ways you can draw this line. I mean, I have drawn one solid line and two dotted lines. Now, intuitively, I mean, okay, so all of these three lines, you can see that this separates it. So what do I mean by separation? So suppose if I take this line, this particular line, this dotted line, right? Now, so I can say that anything that is to the left and below of this line is one class and anything to the right or above is another class, right? Similarly, I can say this for any other line. Now, the first question that we should come to our mind is how many such lines are possible? How many such lines can you draw given these particular object things? Actually, there is an infinite number of lines that can be drawn, right? Because you can see that I can keep on drawing as many lines as I want. So each of these lines is called a decision boundary. Why it is called a decision boundary? So just to complete, so suppose if I draw this line, whatever I'm drawing in red now, I can call this as a decision boundary. Why? Because this is the boundary of decision. If it is above it, then it is one class. If it is below this, then it is the other class. So this is where the decision changes. So this is the boundary, like boundary between, let's say, India and Nepal or something, right? So this is a decision boundary. Now the question is, of all these decision boundaries, we want to find the one that maximizes the margin. So that is why this is called a maximal margin classifier. So maximal margin classifier. Now, of course, when I say it maximizes the margin, I need to understand what is a margin. Now, so a margin is the following thing, is that if this is the decision boundary, what is the margin? That I can do an error up to this part, right? Because if I pull the decision boundary beyond that or beyond this, then I will be misclassifying this circle objects as square. And similarly, my margin on this side is only this, right? Because if I push the decision boundary above by this amount, then I will be misclassifying this uh, the square object as this one. So this is intuitively my margin. And now you see that out of these three lines, this line number 1, line number 2, and line number 3, which one is better? Of course, line number 2. Line number 2 is better because the margins from line number 2, these are the margins. These are the margins. These are the margins. These are actually much larger than the margins for either line number 1 or line number 3. So we want to find this margin. We want to find this decision boundary that has the largest margin that separates these two classes. Now, one assumption that should be clear already is that we are assuming that the classes are linearly separable. For example, there may be a data set like this, right? There may be a data set like this is one class and the other class is like this, right? Now, no line, no hyperplane, now no line can separate these two, the circles from the squares. There is just no way you are doing. You can do it. So forget about maximal margin. There is no decision boundary even, right? You can never do this, right? However, so we are here, the assumption is that the classes are linearly separable. And given that the classes are linearly separable, we are trying to find the one that maximizes the margin. So that is the basic idea of the support vector machine. So the support vector machine in 5 minutes, if somebody has to explain support vector machine in 2 minutes, this is the thing, right? That it finds the maximal margin. Fair enough. So if there are questions, please do stop me and ask. Okay. All right. Now, okay, so we will try to now formalize this mathematically, etc., and trying to understand a little bit more on what does this maximal margin mean. Margin, how to do this. However, one more important point is that, see, even if I go back to these things, so when I say the margin from this solid line is, when I drew this, I actually was only bothered about this point, maybe this point also, or these points, right? So I am not worried, or I am not bothered about this point, or I am not bothered about this point, or I am not bothered about this point, I am not bothered about this point, etc. Why am I not bothered about these points? The reason is, well, I am looking at the minimal margin. I'm looking at the margin, right? So the margin is the minimum distance after which a point shifts, right? So now I know that this point is not important, because if this point shifts, by that time already many other square points have already also shifted. So I do not worry about them, right? I do not worry about these things that are far off from the margin, right? Okay. So this is formalized in this next slide. So the ones that decide what the margin is, these are these black points, right? I've just made them black, right? So these are these things, right? So these are what called the support vectors. So the whole thing is determined by this. These are called support vectors, so objects that are closest to the decision boundary. And this is also the reason why this whole framework or this thing is called support vector machine. So this is a machine that finds its support vectors. correct? So importantly, I'll repeat. So the optimal decision boundary, so the best decision boundary, optimal in which sense? That one which maximizes the margin, right? So the optimal decision boundary and of course the corresponding maximum margin depend only on the support vectors. Okay, they do not depend on these things. So what I mean to say is, even if there is another point here, or this point was not there, or this point was not there, or a point here, or a point here, or a point here, it doesn't matter. The max, so the best decision boundary remains this line. Remains this solid line, right? It does not change. So the best decision boundary, what is the best decision boundary, depend only on the support vectors. They do not depend on any other point, right? So these are the most important objects, and that optimal decision boundary will not change unless, of course, support vectors are changed, right? So and other objects do not influence the decision boundary. All right. I hope things are clear up to this point.
So there is a one question from Gaurav in the chat box. He wants to ask that if the objects are required to be linearly separable, and else SVM will not be applicable.
Good question. I was expecting this. So yes, we will see that this is still applicable. This is just an assumption to build the SVM, and we will see later on that when classes are not linearly separable, whether SVM is applicable or not. But a very good question, and we will see the answer to this in the course of this session. Okay, but I am glad questions are coming. Yeah, this is a good question. Okay, all right. As of now, initially our assumption is that the classes are linearly separable, but we will see later on whether anything can be done about it. Okay. Okay, fine. So now let us move on to a little bit of mathematical formulation of this. Now SVM is easy to understand the basic concept, but to work out the details, there has to be a little bit of mathematics. But I'll try to minimize the mathematics as much as possible. Okay, I'm actually not going into too much of these things, but so that you are just familiar with the ideas, that's why I'm just having a couple of slides of this. Okay. So first thing is that, now remember, this is the notation that we will be using. So each object is a vector represented as xi. So ith object is an xi. So why am I calling it a vector? Because you see there are, I mean, in this example there are two dimensions, right? Dimension 1 and dimension 2, but in general there can be multiple dimensions. So an xi is essentially, it's a xi, the first dimension of this point, the second dimension of the point, and so on and so forth. Right? This is represented as this. So this is a vector because it has got these dimensions. Okay? And as associated with each object is also, there is a class of it. So the class yi is the class. I mean, see, if there are two classes, then there are only two values of yi, right? This is a binary class. As I said, I started off with the assumption saying that this is a linearly separable binary class problem, right? So if there's a binary class, so there are two classes. For mathematical convenience, this is just for mathematical convenience, for nothing else. Let us consider these classes to be +1 or -1. That's it. Instead of calling them 0 and 1, for mathematical convenience, I'm just calling them +1 and -1. See, this choice is in my hands. I mean, I have two classes, so I can call them whatever I want, and I will choose the one that is the most easy for me to work out the mathematics of this. So essentially, now let's see. So basically what I'm trying to say is this, that these square objects, let us say these are +1, and these circle objects, let us say these are -1. Okay. Now intuitively, if this is +1 and this is -1, the boundary, exactly on the boundary, this should be 0, right? Because this is negative side and positive side, it flips over. So this should be 0. Anyway, but what is this that is 0? So this is the equation of a line, right? This is the equation of a line. Now from whatever class 6, 7, 8 geometry, we remember that if there is an x-axis and a y-axis, what is the equation of a line? So suppose I draw a line. I mean I draw this line. What was the equation of a line? The equation of a line, if you remember, ax plus by equal to c, something like that, right? Or let's say ax plus by plus c equal to 0. I mean without loss of generality, correct? So basically I can write the equation of a line as ax plus by equal to c, or we actually said y is equal to mx plus c, but that is an equivalent form. Now remember, what is x and what is y? These are the dimensionalities, right? So what are the dimensionalities here? This is the x1 dimensionality and the x2 dimensionality, right here. So basically what I can say is I can write it as w1 x1 plus w2 x2 and plus some b equal to 0, right? This I can write down as the equation of a line. Now what is w1 x1 plus w2 x2? This is the same as writing it down as a dot product, wx plus b equal to 0. Now all of you are familiar with dot product. What is dot product? So there is a vector w and there is a vector x. So the dot product meaning you take the first component of w and multiply with the first component of x and so on and so forth. So w1 x1 plus w2. So this is the equation of a line, right? Now what do we want? We want the equation of this line to be exactly 0. So that's why we are saying wx plus b equal to 0. This margin, we will say that this is w dot wx plus b equal to plus 1, and this margin on the other side we will call it wx plus b equal to minus 1. This is what we are calling it, right? Because we want this to be done. Okay. So essentially the support vectors are sitting just on these margins, right? So therefore the support vectors is wx plus b is either plus 1 or minus 1. So this for here this is plus 1, for here this is minus 1, and the decision boundary is wx plus b equal to 0. This is the decision boundary. Okay. Okay. Good. Now okay. Now for every other object, that means, so we are assuming that if this is the margin, we are assuming that nothing is in this space, right? In this space between 0 and plus 1 and 0 and minus 1, there is nothing in this place. So whatever is in this space is either greater than plus 1 or less than minus 1. So it's either greater than plus 1 or less than minus 1, right? So depending on which class it is. So we can simply write this I mean in one go as like this. This is can be simply, I mean just right. So this is the I mean this is the setup, the mathematical setup of these things. Okay. Okay. So now what is the margin? What is the actual value of the margin? Now the actual value of the margin, what is the margin? The margin is this distance, right? From assuming there is a point here and assuming there is a point here, this is the margin, right? This is the margin. Now what is the equation of this point here? U is wx plus b equal to plus 1. And what is the equation of this v? It's wx plus b equal to minus 1. So what do we want? We want this u minus v. This is w times u minus v, that is equal to 2, right? Because it's just from the equation plus 1 minus 1 like this. So what is the margin? The margin is the distance between two. Sorry, is there a question? Sorry, is there a question? No. Okay.
Participants, please unmute. Please mute yourself.
Yeah.
Prashant, please mute yourself. Prashant Chaturvedi, yes.
Yeah. Okay. So the margin, the what is the length of the, so the margin is the length, right? So what is that length? It's just u minus v, the length of that that value, right? U minus v. So if w dot u minus v is equal to 2, then the margin is essentially d is equal to 2 by the whatever the value of w is, whatever the norm of whatever the length of the w is, right? U minus v is just w. So basically this is the margin, right? Now remember what, so the margin is this, correct? So the margin is 2 by w. So remember what did we say? We wanted that margin that is maximum. So of all the lines we want that margin that is maximum, right? So we want this d, which is 2 by w, to be maximum, correct? Okay. So then that is precisely what the SVM problem specification is. So SVM tries to maximize this margin D. Okay, all right. So basically, D is equal to 2 by W, right? So when I want to say maximize this value, that is equivalent of minimizing the reciprocal of this. So that means equivalent of minimizing W by 2, or because W is the length of a vector, I can say I can minimize the W square because the solution does not change, right? Again, Y square because of mathematical convenience. So basically the SVM problem is I want to minimize W square by 2, of course, subject to this constraints, right? So I just cannot choose any W, but I have to maintain this constant that every yi times this value wx plus b is greater than 1. So if yi is plus 1, that means this value is also plus greater than 1. If yi is minus 1, that means these values less than minus 1. Right? So the constants are on the objects, correct? So these are constants on the objects, right? So this is the whole SVM problem specification. So this is what is called the SVM problem. Okay. Now this is in the realm of optimization, mathematical optimization. This is a convex quadratic problem, and this can be solved and using these Lagrange multipliers and all those things and Karush-Kuntaka conditions and all those things. We will not bother about it. We'll just assume that mathematically there is a solution to this. So once you train an SVM, there are these packages and lots of softwares available, right? This is what they try to do. They actually try to mathematically solve this. Of course, we will see, I mean, just we'll see that this is not really what they're trying to solve. We are solving a very equivalent problem, but the idea is that this is what solving an SVM means. This is what finding the maximum margin means. Okay. So are there questions in this up to this part? Okay. All right. So now, okay, fine. So when I say you use these Lagrange multipliers for each object, okay, so basically that can be translated into saying that, well, I need to find those multipliers lambda I for all the objects and the b, because remember the equation was wx plus b. The decision boundary is wx plus b equal to 0. So I want to find this b. Okay. So without going into a lot of mathematics, etc., and if you can just believe me at this point, of course you can verify it yourself later on, but you can just believe me at this point. This margin, this W, can be written down in terms of these Lagrange multipliers. So this summation of all the lambda i's yi times xi. So this can be written. I am not giving a proof of this in this session, but this you have to kind of believe me. Okay. So this is on belief. So please believe me. Okay. If you believe me, then we can move forward. If you do not believe me, then I have to prove it, but I'm assuming you all believe me at this point in time. Okay. So if this is the W I have found, now remember, what are we trying to do with SVM? We are trying to classify an object. Finally, our aim is classification, right? We are doing mathematics, we are understanding all this, that is all fine. But finally, we want to classify an object. What does classification of an object mean? Is that we need to tell it whether it is in +1 class or the -1 class. Remember, this was the SVM thing, right? There is a decision boundary like this. So this side is +1 and this side is -1. So given an object here, we need to say that if it is on +1 side, then we call it that, okay, oh, this must be a square. If it is on this side, this -1, then we call it this thing. So what do we essentially want to do? We want to evaluate this W times XQ. XQ is the object that I am trying to test, right? We want to evaluate this WXQ plus B, because depending on that value, now, so all that we are interested is in the sign of this, right? If it is on the plus side, then it is a +1 class. If it is the minus side, it's a -1 class. So all we are interested is the sign of this thing.
अभी आ रहा हूँ.
Sorry. Okay. So all that we need to do is this W times XQ plus B. Correct. Now I can substitute this entire W here in this equation, right? And therefore I get this. So this is for the entire W, right? Up to this part. So this dot product, so W dot product with XQ, so that is dot product with XQ plus B. So I have already solved lambda I have already solved B, so I can do this, right? Because I know the values of lambda i's, I know the values of B, and I know the values of yi, I know the values of xi. Of course, these are given to me. These are the training objects that I originally started off with, and therefore I can find this. Okay. Okay. Now, a couple of questions should come. So this summation involves all I. What does all I mean? All the objects that I started off in the training session, right? So I have given some things in the, I've given some objects and then I found the boundary between them, and that was become my SVM machine, and that's the thing, right? So this all I is over all those objects, correct? So if I had these things here, how many, this is 4 here and maybe this 3 here, then I this, or maybe this is 5 here, so then this all I is over all those 4 plus 5 9 objects, right? So in general this summation, I mean, of all the objects, so if I start with a training with 1 million objects, 1 lakh objects, whatever, this summation is over all those things, right? 1 million. This seems to be not a very nice idea. However, as can be shown that, again from the mathematics, I'm not going to prove this, but again it can be shown that only for the support vectors, this lambda I is a value that is greater than 0. For every or all other objects, lambda I is equal to 0. This is a very, very important part. See, I'm saying for all other objects that are not support vectors, is lambda I is equal to 0. So lambda i's are going to be 0 for all of this. So even if I start with, let's say, 1 lakh training objects and I have only 10 support vectors, okay, what am I saying? I am saying that of all these lambda i's that I have solved, except 10 of them, all the rest, whatever, 99,990 things, all of this, these lambda i's will be 0. This is what the mathematics will tell you. Now that, what does this mean? If I know these are going to be 0, then summing it up makes no sense, because this whole part is going to be 0, right? I know this is going to be 0. So it makes no sense to sum them up. Therefore, I save that summing it up. Thus, so the complexity that, so what is the thing? The complexity of testing is only the number of support vectors. So for how many things do I need to sum up there? Only these 10 objects, right? Only for these 10 support vectors for which lambda I is not equal to 0, lambda I is greater than 0. Only for them I need to sum up. So this all I actually translates to all support vectors. Okay. So this is at the testing time, of course. For the training time, this is still an enormous job. And training, we will come back. But are there any questions up to this part, or is this clear what we are doing? So why does it, although it looks very scary that this is summation over all I, but this is just really summation over all the support vectors. And in general, the support vectors are much, much less than the total number of objects that we start with. Is this clear?
So there are two questions. One is from Abhishek. He's asking that can we have more than 2 classes in SVM?
Again, that is, I'll come to that. That is again a very good question, and we'll come to that.
Okay, sir. And another question is again from Gaurav. How to estimate values of U and V, and why multiple support vector points are required?
So U and
U and V, sir.
I think there has been some technical issue.
Yes, sir. Yes.
Hello. Yeah. What happened? I do not know. I think I dropped out.
Yes, sir.
Okay.
We are not getting the voice, anything.
Hello.
Yeah,
Are
yeah.
you
Please go ahead. Please go
are
ahead.
you getting the voice now?
Yes, sir.
Yes,
Yes,
yes.
sir. We can hear you.
Oh, I'm very sorry. I got dropped out. I didn't realize. At what point in time did I drop out? That also I did not realize.
Sir, I had we asked you questions that
Yeah,
Gaurav.
I got that question about UV and why there are multiple support vectors. Correct?
Yes, sir. Yes.
Acha, so
Yes, sir. Yes.
let me start answering that again. So okay, so U and V are just any points on these margins. I mean, any points on this from the margins, whatever that support starts that touches the support vectors. Okay, so you can take any perpendicular from this decision boundary, and U and V are these things there, right? So if you connect that, so these are just fictitious points. Okay. Uh, so that U and V is required because the distance from U to V is the margin that we are interested in. Okay. Hello.
Yes, sir.
Okay. I thought I'm getting lost again. And okay, the other question is why there are multiple support vectors. Now there can be multiple support vectors because as you see, even in this example, there are three support vectors, one here and two here. So for this two-dimensional problem, there are already three support vectors. Although there can be other support vectors, so there can be a point sitting right here, there can be a point sitting right here, etc. Yes, it can be that there are only two support vectors, one on either side, but it can be multiple support vectors as well. So there is nothing that constrains it to have only uh, two support vectors. So does that answer the question? Yeah. Okay. All right.
Okay, sir.
So
Yes.
So let me then okay. And then there was other question on does it work only for two classes? Yes, I will answer that later on. But more importantly, now, because again from mathematics, from optimization theory, we can say that since this was a minimization problem to start with, remember what were we minimizing? We were minimizing this w square by 2. Right? This can be turned into a maximization problem using those lambdas and all those things. And it looks an extremely scary thing. It's a very long equation, it looks like. But this is what the maximization problem is. Very, very important thing to remember is that forget about the scary part. Just focus on this part. So this is an xi dot xj. Okay. This is a dot product of xi dot xj. Now, what is an xi and what is an xj? These are the training things, right? So now, this formulation has only dot products. It does not use the vectors themselves. So it never uses xi separately, never uses xj separately. It only uses the dot product of this. Of course, this is over all I and all j. That means if I start with 1 lakh objects, this is 1 lakh times 1 lakh, which is a very large thing. Yes, agreed. But it only uses dot products. This is the equivalent dual problem formulation. Okay. The rest of the mathematics is not so important at this point in time. Okay. All right. And we will, why we have done this, we will come back to it later on. But now, first things first is that, so if the classes are linearly separable, so I'm coming back to the questions now. Okay. So if the classes are linearly separable, then of course the SVM builds a classifier that is correct for all training objects. Now the classes may still be linearly separable, but something may happen. This is called noise. Okay. So noise meaning, now you look at this example a little bit more deeply. See, this was our original points, and here is a point which is, of course, this is still of this class, what do you say, square, but this is noise in the sense that this is too close to the boundary. And similarly, there is another point here which is noise, which is too close to the boundary. So this was our original boundary. Okay, so this was our original boundary, this line. And now suppose that there is no original boundary. Now if we just use all these points together, and the decision boundary that we will get is this one, right? This one is the decision boundary that we will get. Okay, because this we have to separate them all nicely and all those things, because this has to be 1 and all those things. However, importantly, if we assume that these 2 points do not exist, let us for the time being assume that these 2 points do not exist, then we get back our original decision boundary, that the original thing, that this is the one. Okay, now you see what is the comparison between these two things. So one is this blue line, the other is this red line. Okay, now once we have this red line, yes, it separates it nicely, but then the points are sitting too close to the red line. For the blue line, that is a much better separator. It looks like a much better separator, but of course for the blue line, what we have done is we have ignored these two things. Basically, we have said that look, these two things are too close. These two things look like noise. These two things are not really very important. So we ignore them and build the classifier, and later on we handle them. Okay. So the boundaries and margins and all of these are closer. However, more importantly, what happens is that if we now say I am using this blue line, and this is your +1 line, right? And this is your -1 line. This is from that this thing. Now you see this point is sitting within that +1. So remember, we said that yi has to be greater than +1 for this. And similarly, this point is sitting within -1. Again, for the negative class, we said this should have been less than -1. Now these two things are failing for these noise points. This is not greater than +1. This is actually less than +1. And similarly, this is not less than -1. This is actually greater than -1. Now to do that, what we do is that, okay, we will add what we call as slack. We will add a little bit of slackness. This is a little bit of looseness, right? We are not so tight on +1 and -1. We are adding this xi variable slack, and we are saying, okay, it may not be +1 and -1, but it is, as long as it is beyond some slack, 1 minus some xi I and 1 minus xi I less than, we are happy. So together, for every object, we are not making it strictly +1 or -1. We are adding a little bit of slack. This is the slack. Okay. Why are we doing this? Because this helps us build a better classifier, overall better classifier. Because by ignoring some noise points, we can do a better classifier. Okay. Okay. Good. So now rest of the things remain more or less similar in the sense that this margin is still 2 by W. So this is called a soft margin now. Why this is called a soft margin? Because you see this is not between +1 and -1 any further. So it's a soft margin. It's a little fuzzy. However, more importantly, this cannot be simply minimized anymore because why this cannot be done anymore? Because the SVM, while it is building this, it will not know which one is noise. If you say anything can be noise, it will say, well, everything is noise. And then it will build a degenerate classifier saying, oh, everything is noise. I do not care. So this cannot be done anymore. So because this will end up saying that too many objects will be just saying noise, right? Everything will be noise. So that means too much slack will be added. So you need to protect that. So basically what is being done is that you have to say that I minimize this fine plus the slack plus some function of the slack. So that means I cannot add too much slack, because if I add too much slack, this quantity keeps on increasing. Therefore, the minimization problem, it will cause this thing. So I have to guard against too much slack. So I just cannot say everything is noise. So this is generally what human beings do, right? Once in a while, you are on diet, you may say, well, once in a while I may eat an ice cream because there's a special day, something noise day, etc. But if you say, I can keep on eating ice cream any day, then the diet makes no sense, right? So once in a while it is okay to do it, but not too much time. So you're just guarding it, that's all. So that's just the problem with slack. Okay. Now comes this big question of, so if the data is not linearly separable, then what happens? Correct. So what is an example of not linearly separable data? Say, for example, the data is like this. This is not linearly separable, right? There is no way this is linearly separable. But we may assume that there is some non-linear boundary that separates it. What is this non-linear boundary? This is a circle, right? So let's look at this example. So this is your x1 dimension and this is your x2 dimension. Although this is not linearly separable, this is non-linearly separable. This is separable in a non-linear manner, right? So this is a non-linear boundary. There is a non-linear boundary to this, which is the circle. What, by the way, is the equation of a circle? Hello? Am I there or not? Hello?
We can hear you. Go ahead.
Okay, yeah.
Yes.
Yeah, I was very worried.
Yes, sir.
Okay. Equation of a circle is what? Essentially, it involves x square, x1 square, and all those things, right? Now, very importantly, so let us say the equation of this circle is, if suppose this is the center point, this is the radius, the center point. So what do we do? What is the equation of a circle? This is x minus a whole square plus y minus b whole square is equal to some r square, right? That is the equation of a circle, correct? Now here, as I said, this is not x and y any further. The dimensions are x and x2. So basically you can write this whole thing down saying that there is some x1 square, there is an x1 sum with some value plus some x2 square minus some x2, and then there is some constant, right, which is equal to 0. So you can observe all of this. So what I can do is I can now treat this x1 square minus x1 as a new dimension and x2 square minus x2 as a new dimension. Okay, I can treat this. I can do this, correct? If I do this, so let me call those dimensions are x1 dashed and x2 dashed. Then what does the equation become? The equation becomes x1 dashed plus x2 dashed plus c equal to 0, right? Correct. Now I can say that, well, that means this is linear in this space, right? This is just linear. This is just x1 dash plus x2 dash plus, of course, some constants, right? So what am I trying to do is, instead of plotting the point in this x1 and x2 dimension, if I plot it in this x1 square minus x1 and x2 square minus x2 dimensions, then I get some new things. So these points will become here, this point will become there, and so on and so forth. This point may become there, this point may become here, this point may become here, and so on and so forth. This will happen, right? What can be then shown is that now in this new space, this becomes linearly separable, correct? This becomes linearly separable now, right? This is a very, very important idea. Is the saying that even though I started off with a nonlinear boundary, after some transformation, this is some transformation, I have made this again linearly separable. What is the transformation that I have done? That instead of using x1 and x2 as my dimensions, I have used x1 square minus x1 and x2 square minus x2 as my dimensions, because I know this is a circle and so on and so forth, right? Correct? Now, once you are in this space, this becomes linearly separable, then you can use the standard SVM method there directly. So, to answer that question, that what happens when the classes are not linearly separable? Then the question is, if there is a transformation that takes it to some other dimensions, some other space, where this is linearly separable, then you can apply the SVM in that new space. The question then is, can we find this transformation? How do we find this transformation? But we can, once we can find this transformation, we are done. We can just apply the SVM. Right? Is that clear? Is this clear? Is there questions on this? Any questions on this?
Sir, I have a question in this. In this, you have taken it a circle, like you have separated these 2 points using a circle.
Right.
But it's not always essential that we get a circle or we can apply a circle equation to it. Maybe it's some other ellipse or a parabola, then in that case, what will happen? How are we supposed to know whether we have to use a circle like a separation or what?
Fantastic question. Fantastic question. Although I was expecting it. So actually, so some points, right? And suppose the other class is like this. So what is the equation? The equation, you may say this is some complicated parabola kind of thing, right? Yeah. But suppose now I put in another point here. Then you have to say, oh no, this is not parabola any further. This is another, maybe some very complicated thing, right? So the question remains the same, that how can you guarantee that a circle or a parabola or a hyperbola or whatever, or ellipse or whatever will fit? How do you know that? Right? And that's again a very good question, and I will come to that answer to that. Okay, let's see. So here is, just to complete the story, this is that example. So you can actually push it like this, that x1 square, so that you can say that the radius is like this, and this becomes linearly separable. So then we are grappling with this question. So right now the answer is, if there is such a transformation phi, then we can do SVM very well. But the question is how to find such a transformation, or who tells us that there is such a transformation? Is there a guarantee that such a transformation exists? So now the theory comes is that this is, of course, by the way, this is not an obvious and easy question. So there are 2 ways of answering this. Is that first of all, assume for the time being that there is such a transformation. But the transformation may be very costly in the sense that the transformation may result in a very high dimensional, or actually mathematically it can be shown that this can be an infinite dimensional space. Well, what is an infinite dimensional space? We cannot comprehend probably, but mathematically is that just that you require an enormous, infinite number of things to separate them out, right? Now, even if it is not infinite dimensional, let's say we are grappling with a finite set problem, right? So we have a finite, we have, let's say, 1 lakh objects. So it cannot be anything more than 1 lakh dimensional things. It is at most 1 lakh dimensional, let's say. But a 1 lakh dimensional object you cannot process, right? That's how to use an SVM then. It's a very, very hard thing. Even if it is a very, very high dimensional thing, how to process it? So there are two questions. First of all, it's a mathematical question, is whether such a transformation exists. And then there is an engineering question, that even if such a transformation exists, can we use it practically? So I cannot say that, okay, I will give you a very nice SVM, but I will take, this is a 1 crore dimensional thing. So give me an SVM problem. I will give you the SVM next year. By that time, please sit down. I am solving my mathematics. That is not a nice way of doing things, right?
Yeah.
So, yeah, please, question.
अच्छा होमोग्लोबिन बढ़ जा रहा है और
What? I think there is some background noise coming, so please mute yourselves, please. So okay, so how to this thing this? So by the way, so just to answer the first part, the mathematical part of this is that it can be shown that if there is a finite number of objects, which is what we will do in computer science, we are never going to do anything other than this. If there is a finite number of objects, finite number of training objects, then such a transformation always exists. Then transformation always exists, right? So the mathematical part of the question, the first part of the question is answered, right? This always exists. Okay, that is fine. That is fine. But the question is it practical enough? Okay. So for that, what is called a kernel trick is being used. This is a very, 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 very important idea, and this is a very, very famous idea for SVM. This is what the kernel trick does. Okay. So a kernel, very, very simply, forget about anything else. A kernel is a function that computes the similarity between two vectors, right? So you give a vector and give a kernel function, two vectors, it will compute. Just for example, you take 2 points and take the Euclidean distance function. That is, so Euclidean distance can also be considered as a kernel, right? So just any function. Now, now we go back to that dual problem formulation. If you remember, the dual problem formulation required that we only use dot products. We do not use either W or the product or the objects themselves. So remember, dot products meaning all we need is xi dot xj. If we can compute this, we are done. We do not require xi separately. We do not require w separately. So we do not require this. All you require is the ability to compute xi dot xj. Now, what I'm trying to say is, suppose this the transformation that we are talking about is phi. That means what was an object xi now will become phi xi. This is some transformation, and this xj will become phi xj, right? So previously, whatever was xi dot xj, this dot product, this is your phi xi dot phi xj. This is just this dot product that we require. This is all that we require. We do not require, very, very importantly, again, please understand this is important. We do not require the values of phi xi and phi xj separately. All we need is directly, can we compute phi xi dot phi xj? This seems a little counterintuitive, right? Basically, what I'm trying to say is, oh, you do not require an apple and an orange, but you will require the product of apple and orange. So I will give you a direct machine to compute the product of apple and orange. even if you do not tell me what, even if you do not give me the apple and orange, right? Well, but that is what this is it. So the kernel function, that is where this is called the kernel trick. This is the trick, that the kernel function is that if you give it the original points xi, xj, there is some function kernel that is equivalent to the phi xi dot phi xj of these things. Okay, let's move on to an example directly, and then that will be clear. So here is, so suppose there is this vector u and v. These are of dimensionality n. Okay, some dimensionality n. This is what you are doing. So suppose your transformation is like this: phi u and phi v. This is the circle transformation. This is just an example, by the way. Please don't assume that everything is a circle. This is just an example, right? So the circle thing says that you will require u1, 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 u2, u1 up to un, un. Then you will require square root 2 u1, square root 2 un. This is the transformation, right? And this is the transformation. Correct? Now remember what we are doing. We are doing phi I dot phi v. So phi I dot phi v. If you do that, actually phi I dot phi v, and if you that, it can be shown to be equivalent to u dot v plus 1 whole square. Simply u dot v dot plus 1 whole square. Remember, so this is the kernel function. This kernel function does not require phi u and phi v. It only uses u and v, but it gives you the equivalent of this. So this is the equivalent of this. Okay, because I mean, this can be just checked. If we just multiply, if we just take the u dot v, the dot product of these two and do it, this can be shown to be equivalent of this. So what is done? So very, very importantly, so that see the phi u's, that these dimensionalities are large, n square plus n plus 1, right? So if you started off, let's say a 10-dimensional vector, this phi u and phi things are what, 111 dimensional vectors, right? But instead of 111 dimensional vectors, we're still just doing 10 things. But more importantly, this shows a shortcut way. So the kernel function directly gives you a shortcut way of having the transformation and getting that dot product. Okay. So yeah, any questions on this? This I mean, I can expect a little some questions in this. So the kernel is a shortcut way of getting a dot product, because the SVM does not require the phi's. I am repeating, the SVM does not require the transformation per se. It does not require what is phi xi or phi xj. It only requires to compute phi xi dot phi xj. Right? So if there is a shortcut way, which is your kernel uv, that directly, the kernel xi xj, let's say, that directly computes the dot product, then you are done. You do not require transformation there. Right? So that is what the kernel is doing. Okay. Fine. This is the kernel trick. The question still remains is that how do we find the kernel then? Now the question is becoming, instead of finding the transformation, can we find such a kernel that computes the transformation? So again, the answer is, can we find such a kernel? Is it guaranteed to find such a kernel? Can we always guarantee to find such a kernel? Well, we cannot. That is, there is no guarantee, but there are 3 popular kernels that are used in practice, and they solve most of the problems fairly well. They may not be solving everything, but they can solve most of it problems. Right? So first is called the polynomial kernel. The polynomial kernel is, this is a kernel function, that this is u dot v plus 1 to the power of h. So this is a generic polynomial kernel, right? So if h is equal to 2, you can call it a circle, but this is a generic polynomial. Basically, this is any polynomial, this thing. Right? Then there is a Gaussian radial basis kernel. This is depending on your Gaussian curve, that e to the power minus this thing. You see, this is some complicated exponential of these things, but this is again another kernel. And then there is another called sigmoid kernel. This is again this is a hyperbolic tangent function of that u dot v minus some scaling and transformation, etc. So these are 3 popular kernels that are mostly used, but these are used kind of blindly. Please to understand the difference. See that, so saying that I am not sure whether a circle solves it or an ellipse solves it or a Gaussian kernel solves it or etc. I have no idea. So I am not doing it. Therefore, I am just assuming blindly that I assume that a Gaussian kernel solves it. And then you apply that and then you try to solve the problem. Or you assume that a polynomial kernel solves it and you do that. So this assumption may be wrong. So you may not get a nice solution. It may not get very good results. But if that assumption was right, then this polynomial kernel solved it quite nicely, quite quickly. Right? So does that answer that question of can we find such a transformation? Are we doing this circle, etc.? Please, I'd like to hear back from you.
Yes, sir, definitely. Thank you, sir.
Okay. All right. So this answers the question of what if data is not linearly separable, right? And what if we find transformation and all those things? The other big question that remains is what if this is not a binary class problem? What if this is a multiple classes problem? So I started off saying, oh, this is +1 class and -1 class, and that's all that we can do, etc., etc., etc. Of course, most practical problems are not binary classes. There are multiple classes, right? So can we solve it? Well, there are two generic ways of solving it. First is 1 against 1. That means every class is compared against every other class. Okay. So that means there are m square comparisons, order m square classes, this thing. So if there are 3 classes, let's say class 1, class 2, class 3, then we first build an SVM classifier which is C1 against C2. Then we build another SVM classifier which is C2 against C3. Then we build another SVM classifier which is C3 against C1. Right now, once a test object comes, we pass it through all these 3 things. Right now, suppose C1 against C2 tells you that this is C1 class. C2 against C3 tells you that this is C3 class. And C1 against C3 tells you this is C1 class. Then what is my conclusion? What is the class? This is it. This is majority voting. So we will say C1, right? Correct. Any questions in the here? Well, there's an obvious question, right? So suppose this calls it C2 and this is C3 and this is C1. Then what do we do? So everyone gets 1 vote. Then what do we do? Okay. Now you see, here is the idea. So C1 and C2, when we say this is C1 and C2 classifier, and we call it C2, we essentially find the point how far this is off from the margin, right? And then we have a C2, C3 classifier, and then we say this is C3, say this is here, right? And then there is a C3, C1 classifier, and then let's say we have the point here, right? So if this is the situation, okay, which one, all of them gets 1 vote each. So C2, C3 and C1, all of them get one vote each. But which one would you now classify? Well, C1 is farthest away from the margin, right? So that means you are the most confident about C1. C3 is very close to the margin, so it could have been C2 also. Again, here C2 is quite close to the margin, so it could have been C1. But here C1 is farthest away from the margin, so I am more confident about C1 because this is farthest away from the margin. This is very far off. So to topple this, I have to traverse a lot of distance. So then my answer is here C1. Because of
So in this case, we'll have to find out the distance vector, etc. also to find out that which is the farthest one.
Precisely, exactly. So in this case, originally I started off saying this is the sign of Wx q plus b, right? So now I cannot use the sign. I have to use the absolute value of this, right? How far this is it? So this is the absolute value. So w times xq plus p. This is what we have to use. Exactly. Good question. So we cannot use the sign any further. We have to actually find out these things. Because this is multiple classes, we have to extend SVM. Just binary class, we are happy with the sign, but this is extension, right? This is one way of doing it. This is one against one. The other is one against all, one against others. So what we are doing here is, again, assume that there are three classes, C1, C2, C3. Then what we are doing is, we are building a class which is C1 against not of C1. Okay, which means all of C2 and C3. Then C2 against not of C2. Then C3 against not of C3. Now again a test object comes, we may say this is C1, this is not of C2, this is not of C3. So then what is my conclusion? What class is this? C1. Very simply C1, right? But again we may run into trouble. We may say take C1, C2 or not of C3. Then which class is it? Is it C1 or C2? Again, the one that is farthest away from the margin. So assuming this C1 is farthest away from the margin, my conclusion will be C1. And another interesting case may happen is that this classifiers may say, oh, this is neither C1 nor C2 nor C3. Then what is your conclusion? Well, we use the same idea, is that whichever is, well, it is not C1, it is not, it is here, but this is suppose here. So this is how much do I traverse to make it C1. So this is the margin. So whichever is closest to the margin of C1, closest to the margin of the positive class, that is the. So again, this maybe this. So just complete the story. So this is quite deep into not C1 class. This is not very deep. And then let's say C3 and not C3 is also a little deeper. Now, so this is closest to the margin to C1. Therefore, my conclusion is C1. Okay. All right. So in this. No, right. So let us then finish SVM. So we have done. So we can say that, so for finite training set, transformation that separates data linearly always exists, that we said. And then of course there can be some other better kernels. So we are blindly trying one of these three kernels one by one maybe, but there may be some other better kernel, and you may design your own kernel. That is fine. That is okay. Then for large training set, the training time may be too impractical, because you remember this is the dot product of the training vectors each other, x dot xq. There are a lot of vectors, these dot products x1 dot xq of all these pair of objects can be very large. So SVM training time can be very, very large. Now suppose much lesser in general. But the training
Professor,
time.
your voice is distorting, Professor.
Okay, okay. Is it better?
Yeah, now it's better.
Okay. So I was saying the training time may be very, very large, because it computes the dot product of pairs of objects. Pairs of objects may be very, very large. Training time may be large, although the testing time may not be that large. The testing time is dependent only on the number of support vectors, which is proper in 100. And now I give you 5 more objects. Now you have to rebuild that entire SVM. You cannot take that SVM that is built with 100 objects and absorb these 5 objects somehow. You cannot. So you have to rebuild this. So that means this is not incremental. So any new thing comes, you have to redo that entire thing. Okay. It also suffers from this class imbalance problem, in the sense that if one of the classes have got many more values than the other class, it suffers because it takes into account that noise and all those things. So the one of the classes may simply be taken as noise. It will not do a good job of doing that. And it protects against this. So this noise or slack is important because that guards against overfitting. Even nonlinear kernels can overfit, but this slack guards against overfitting. But that is why it also suffers from this class imbalance problem. Okay, and that's about it for this session. My email address is already visible to all of you, I am hoping. So if there are any questions now, please do ask, or you can also later on ask questions. Hello.
Hello.
Yes, Professor.
Yeah. So if there are questions, please ask. We have about time for a couple of questions, 10 minutes of time.
Yes, participants, anybody, any question, you can unmute yourself. Okay, since we do not have questions, I think that's okay, Professor Annam.
Okay. So thank you all very much. So as I said, if you want, if you come up with questions later on, please do not hesitate to ask me. You can always email me. Okay.
Yes, we'll surely send the email.
Thank you, and I'm sorry for these multiple internet problems and team problems. This was not in my hand. I'm sorry for that. But I hope you have enjoyed the session. You understood about SVMs. All right then.
Thank you very much, Professor.
Thank you.
very
Thank
much.
you. Bye bye.
Bye. Okay, participants, we come to the end of day 2 with this particular session. I would download the attendance for this session from the MS Teams itself and appropriately consolidate in my Excel records. Thank you very much. We meet tomorrow at 10 o'clock. The fresh links would be again mailed to you as and when. Today things have gone smooth. That's good. Thank you very much, and goodbye all of you. Thank you. Abhinav, I think you can end the meet.